So the next presentation is on artificial intelligence, Stephan Griebel. So Stephan, are you online?
Yes, can you see and hear me?
Hello, yes, we see you. Perfect.
Hello.
The floor is yours.
Thanks a lot, and thanks to everybody for having me at this ICT for Railways. I have to admit that I'm very honored to be part of that today, because for years I have been watching the ever-growing importance of this meeting of the ICT, and also in TC9X we very intensively talked about this. So thanks a lot for having me today, and that I can participate with my scarce knowledge about artificial intelligence and standardization, which I want to talk to you about today. This is based on a report also we had at the Senelec Signaling Committee, SC9XA, together with the UK chairman Roger Short. So next slide, please. Okay, there's a little delay. So I'm the, besides my normal work at Siemens Mobility as a RAMS engineer, RAMS expert, I'm the Senelec chairman for the railway signaling. I'm working in Germany for the Siemens Mobility company for 20 years now. I'm in Siemens internally. I'm the chairman of the Siemens expert group on artificial intelligence and safety. And I'm also the German chairman for the railway signaling. So I have to admit that I can't deny some responsibility of what is going on in the standardization committees when it comes to, for example, DKE, the German committee, and the European signaling committee. Next slide, please. The topic of today, you can click 3 times, then we have the whole display. I don't want to make it too complicated. So the whole abstract would be already, so the management summary would be that when it comes to artificial intelligence, however it is defined, we will come to that later, also including machine learning, there are fascinating applications right now in the field also of railways, surely enough, mainly focused on diagnosis of preventive maintenance on RAM aspects. And there are some first timid steps into also certification when it comes to safety. And that I like to focus a little bit on today, because my second message would be that there are, for electronic systems, I only can speak for electronic systems, I'm not a mechanical guy. So from railway signaling point of view, we have very elaborate safety standards that also cover software aspects. And surely enough, they will remain in place and be, let's say, the bottleneck, even for algorithms that deal with artificial intelligence whenever safety is involved. That would be my main message. Yet we have to recognize that the existing standards might not cover each and every new aspect that comes with the application of machine learning. The tricky thing is that, as always, some hard problems when it comes to artificial intelligence and machine learning remain to be solved, but that's what research is for, isn't it? Next slide, please. That's just a marketing slide about the various gazillions application fields you could use artificial intelligence and machine learning in. So we can skip that, because I was also told to be very brief and succinct. You might have noticed that when it comes to artificial intelligence, it features on, let's say, every second slide wherever you look at. So left, right, and center, we have these artificial intelligence themes. And I have to out myself as a mathematician. So I was very interested in what's behind the slides and what are the real algorithms mathematically about. And that's very, very fascinating, but I hope I don't have to make marketing for that. What I like to come across, to bring across with this slide, is that especially machine learning is part of artificial intelligence. Artificial intelligence in general, there are a lot of definitions, but seems to talk about the ability of machines to simulate human behavior and to mimic cognitive functions. That seem to be also characteristic of humans. And there are also logic analysis, there are expert systems involved, but also the so-called machine learning. And I like to focus on this subgroup. Machine learning means the automatic adaptation of machines in order to learn and to approximate functionality, without having been explicitly and deterministically programmed for that. So basically, it's very, very sophisticated statistics. It stemmed from the last millennium, the 50s of the last century, but now the thing is we have the power when it comes to calculation in order to make them really fruitful and useful. And inside then we have, as an example, also the neural networks, which you might be familiar with, and the perceptron as one special example. Okay, so you know, in terms of definitions, we could spend years. We don't have this much of time, I was told. So thank you. Next slide. You can read my, adapt to my speeding of my speech speed. Thanks a lot. So what's the main difference between classical program and machine learning, now this subgroup? I know there are various variants of machine learning here, focus only on the supervised learning ones. So in classical programming, as you know, you define rules, you program them, you fix them, and then you fill the data into these rules, and then you receive deterministically, so we hope in most cases, the necessary results. That's classical programming. Whereas in machine learning, we said that what you have is you have an algorithm that has a lot of loose screws in it, so a lot of parameters not yet fixed and not yet determined. And what you now do is you take always pairs of data and the desired result in the first phase, so to speak. You have to train and to adapt your machine. You take these pairs and you adjust your machine and the parameters so that the results are very close to what you wish, depending on the input data. And that's how you train your parameters inside these machines that are still loose, and you have to fix them in order to approximate a functionality. Because then in the second phase, in the usage phase, in the operation phase, so to speak, then you give new data and you hope that the result is close to what you want as a trained functionality. So the main difference is that the rules and the functions you have inside the machine learning, they are approximate. There are approximations, very sophisticated ones, yet not in the classical one where you say we have yes, I will go on soon. Not in the classical sense in which you you do your programming. Next slide, please. I already summoned, so to speak, this slide, because how you train a machine. Algorithm means that you have to build a data set. That is, you have to collect data and the desired results. You have to have this as an ingredient. Then you have to have this little machine with the loose screws in it and the loose parameters. And this is developed according to normal software development standards. And then you adopt this, you train, so to speak, these algorithms, and you fix these parameters in order to improve its performance. So the fourth point I've already mentioned. Yes, next slide, please. So what is different about machine learning? First click, please. I should have abandoned the presentation mode. I'm sorry for that. I thought that I was in control. So delegating sometimes is different and difficult. So machine learning implements a software structure which then adapts itself according to the sets and the pairs of input and desired results in the training phase. So it changes itself based on the training data. Then, if we have trained enough, then it's fixed. Yet this also means that as we have only an approximated functionality, which we can't really see and can't really test, that means that we have to abandon this classic thought of functionality that you have defined very precisely, which is then decomposed into various software architecture and modules. So the traceability is not the key concept here, and we can't deal with that anymore and take this into consideration. This also means that it's not easy to achieve the coverage, for example, when it comes to testing and verification methods in a classical sense. And the next point, is there one? Exactly. And given the fact that it's one, okay, perfect. And given the fact that it's all statistics and statistical methods, also least square method basically is and regression is machine learning algorithms. It means that we do not have any longer, as in classical, for example, safety argumentation, this causal relationship between input and output and functionality. What we have is we have to deal with statistical correlations. And that gives some nut to crack, so to speak. Next slide. So these are one of the hard problems of machine learning that remain and are still under research. Okay, they are challenges. We don't have problems anymore, but challenges and opportunities. So for example, the first thing is we have to guarantee or somehow to measure with some key performance indicator how complete, accurate, and statistically representative the training data is. Is it in the same environment as in the operational phase? You can, all the people and the AI expert and data management experts, which I'm not, know gazillions of examples of how important these training data and the correct statistical representativity is. Next point, please. As I said, as I indicated, that verifying the trained software is very hard because you do not have any longer this clear-cut requirements tracing and the breaking down. Next slide. So this then comes to validation of the approximated functionality because you do not have the functionality any longer. The biggest advantage of the machine learning algorithms, that is that they generalize into areas which they have not seen, is also turning into their biggest, not necessarily disadvantage, but downside when it comes to validating functionality. Also when it comes to freedom from random and systematic faults, which is one of the bottlenecks of the safety arguments, this is very hard because there might be not only as in logic, only these two things, but there might be different failure categories which we have not yet captured successfully. Next slide, please. Okay, was too fast. Next point, please. So if you go one back, then we see the last 2 points, but that's fast. Protection against adversarial attacks. They are very sophisticated and elaborated things where you manipulate, for example, when it comes to object recognition, where you manipulate very slightly the picture. Everybody says, that's for example, that's an elephant, whereas your algorithm puts out a completely different thing. But that's AI specific. And the last one is, as I said, missing causality and only statistical relation. Okay, but there's a lot of fascinating research underway. Next slide, please. Those are only application examples, autonomous train, obstacle detections, and driver advanced advisory systems. So the whole industry is buzzing when it comes to these examples. Next slide. So also standardization is dealing with it. Despite the various challenges we still have in research, also standardization is going on. And as my talk has been captured by standardization and I like to briefly show that. So on a worldwide level, IEC, ISO, there's a Joint Technical Committee 1, and there's a very fascinating subgroup that is the subcommittee 42, SC42. And there they are working on a whole panoply of various standards on artificial intelligence, machine learning, neural networks, starting from terms and definitions. So if you have time, you might go into these terms and definitions groups. And then on a European level, we have also Senelec. They had a focus group on AI, and also the European Commission had a high-level expert group on AI. And this also led to the newly founded Joint Technical Committee 21, here marked in yellow or orange, on artificial intelligence. We will talk about that in 2 slides. And also, just to pick out, in Germany, for example, we also have a standardization roadmap AI. So left, right, and center, committees are popping up, even though there are still a lot of nuts to crack. And as Gian Osvaldo, the IEC TC9 chairman, said, standardization also has to cope with these aspects of research and has to adapt because everything is going faster. As is my presentation, so the next slide, please. So on a worldwide level, some details on the subcommittee 42 on artificial intelligence, started in spring 2018, has a lot of working groups, starting from foundation standards, issues of big data, but also trustworthiness. So we would say accurateness, integrity, how often are they wrong, so to speak. Also applications, also governance applications of AI, and also general AI management system standards. So very fascinating, this IEC SE42 group. I'm part of that. I can hardly cope with all the material popping there up. Next slide, please. As I said, on a Senelec European level, we have this Joint Technical Committee 21. They had their second meeting, beginning of, I think, November. What they have now fixed is their scope. That is, they have to produce deliverables in the field of artificial intelligence and related use of data. They have to look also worldwide what's going on in SC42, artificial intelligence. And especially they have to address these standardization deliverables to address the European market and the market and societal needs. Truly enough, upholding the EU legislation and the EU values. And Senelec Railways, we are also fast because we have founded a survey group 34 on digital twin and artificial intelligence. They have been popping up and ramping up, so to speak, with a new scope and a new calls for experts underway. We had 2 weeks ago, I think, or 3 weeks ago, our TC9X meeting, and this now is gaining pace and will be starting soon. Okay, next slide, please. And this also leads me to my conclusions. So machine learning, this subgroup of artificial intelligence becomes viable, also truly enough in the train areas, and when it comes to standardization, SC9XA, the signaling part, is monitoring it, as is the railway overall mother committee, the TC9X. Next slide, please. We see very fruitful and fascinating applications in the field of RAM, that is reliability, availability, and maintainability. Yet, when it comes to the next important steps, there are still a lot of nuts to crack in AI research and AI standardization. Let's say we have to drag and to push at the same pace. So we have to also monitor how these remaining and resisting challenges develop, and when we can do the next steps, maybe also in the safety direction. But right now, I guess it's not the time. And if it were the time, then there still would be the bottlenecks of the existing functional safety standards that are, so to speak, the roof under which every safety-related electronic function has to fit. And that brings me to the end of my presentation. Thanks a lot, and thanks for your attention and having me.